Dijkstra's algorithm is a graph traversal algorithm which also has applications in pathfinding. I'm going to explain this algorithm through an example. So here we've got a map of the UK where I live, and in the UK we have lots of cities like London, Birmingham, Cardiff, and many others up north. I'm going to shorten their names down into single characters since they're easy to work with. Let's say I wanted to find the shortest path from London to Glasgow. How would I solve this problem? Well, the first step is finding all the different routes we could take to get around these cities or to move around them. So let's say these orange lines represent hypothetical routes between these cities. You might notice that there are multiple routes we could take to get from London to Glasgow. We could take, for example, the blue path, which goes to Glasgow from London to Newcastle through Edinburgh. We could also take the green or purple path. So how do we know which path has the shortest distance and is therefore the most optimal? Well, we could use Dijkstra's algorithm to solve this problem. But the first step is we need to represent these cities as a graph. So let's imagine that these cities are nodes on the graph and the routes are edges between them. We can also add weights, and in this case the weights are approximations of the distances between the cities using the routes. Dijkstra's algorithm is quite simple as it only has two steps. The first step is to visit an unvisited node which has the lowest total cost, and the second step is updating its adjacent nodes with values if it's appropriate. And I'll explain what that means in a minute. So we first need to assign a node as a starting node. In this case we want to find the distance from London to Glasgow, so our start node will be London. You might notice that all of these cities have infinity symbols under them except London. The reason is London is our starting node that has a total cost of 0 since we're just starting there. There's no cost to travel there. And all these other nodes are unvisited, so we just set their total cost to be infinity. As we visit them, we can update their total cost accordingly. So we'll start off by exploring all of the adjacent nodes of London. There are currently 4 adjacent nodes: Cardiff, Birmingham, Newcastle, Edinburgh, and the shortest one is Birmingham with a cost of 100. So we will update the information of the Birmingham node with a total cost of 100, and its parent node, or the node it came from, is London. The other closest adjacent node is Cardiff, which has a cost of 150. So I'll update Cardiff as well with a total cost of 150, and its parent node is London. We can also do the same to Newcastle, and it will have a total cost of 250. And the same can also be done for Edinburgh, which is the furthest away, and that will have a total cost of 410. At this point, we visited all of the adjacent nodes of London, so we can mark London as fully visited, so it's green now. We now go back to step 1 of the algorithm, which is finding the unexplored or unvisited node in the graph with the lowest total cost. So here we have 4 nodes which have been unvisited, or rather which have been visited but not fully explored. We have Birmingham, Cardiff, Newcastle, and Edinburgh. So right now Birmingham has the lowest total cost of 100 out of all 4, so we will explore Birmingham next. So I will set Birmingham as the new current node, and the first node we will explore is London. So the cost to go from Birmingham to London will be Birmingham's current total cost, which is 100, plus the cost of the edge, or the weight on the edge, which is 100. So the total cost of going from Birmingham to London, in this case, would be 200. Now you might notice that 200 is greater than 0, so we won't update London's node with a value of 200 and a parent node of Birmingham, because that's not an optimal path. That's slower than what we currently have there. So we will leave London as it is. We will now visit Cardiff. So Cardiff has a edge of 115 and Birmingham's current cost is 100. So the total cost to get to Cardiff from Birmingham will be 100 plus 115, which is 215. Now 215 is greater than Cardiff's current cost, which is 150. So we won't update Cardiff's current cost or parent, since getting to Cardiff from London directly is faster than getting to Cardiff from Birmingham, which is going through London. So we just leave that as it is. And since we've explored all of Birmingham's adjacent nodes, we can mark Birmingham as fully visited and then move on to the next node with the lowest total cost. In this case, it's Cardiff. So Cardiff is the new current node, and it has two neighbours, Birmingham and London. Now, the cost to go to Birmingham from Cardiff would be 150 plus the weight on the edge, which is 115. So that will be 265. Now 265 is greater than Birmingham's current total cost, which is 100, which means that going to Birmingham from Cardiff is going to be less optimal, or it's going to take longer than going to Birmingham straight through London. So we won't update the total cost of Birmingham in this case. And the same applies for London. We won't update it since the current path is optimal. So we can mark Cardiff as fully explored. The next node we will explore is Newcastle. So Newcastle has a total cost of 250 and it has 3 neighbours. So let's look at the first neighbour, which is adjacent cells. The first adjacent cell is Edinburgh. So the cost to go from Newcastle to Edinburgh will be 250, which is the total cost of Newcastle right now, plus 120, which equals 370. You might notice that 370 is less than Edinburgh's current total cost, which is 410. So we can update Edinburgh's total cost to be 370. And we will set the parent node of Edinburgh to now be Newcastle. What this means is it's faster to get to Edinburgh through Newcastle rather than going directly through London. So we found a new optimal path. The other neighbouring cell is unexplored, which is Glasgow. So Glasgow will have a total cost of 250 plus 150, which is equal to 400, right? So we'll set the parent node of Glasgow to be Newcastle and its total cost to be 400. We won't explore London since we already know that the current path to London is already optimal, so we don't have to bother exploring it. We can then mark Newcastle as fully visited, and the next node we will visit is Edinburgh, since it has a lower total cost than Glasgow, which is also unvisited. So Edinburgh is the current node. It has 3 neighbouring nodes. We won't bother exploring London since I already explained it's already the optimal path. To go to Newcastle from Edinburgh would be 370, which is a total cost of Edinburgh, plus 120, which is 490. And 490 is much greater than Newcastle's current cost, which is 250. So there's no point updating Newcastle's total cost. If you try visiting Glasgow through Edinburgh, the total cost will be 415, which is greater than Glasgow's current cost, which is 400. So we won't update it either. Another thing you could also do is that if a node has been fully visited, then we don't have to bother trying to explore it because we will know that it's the optimum path, just through how I showed you guys before. So we can mark Edinburgh as fully visited, and then we can move over to the last unvisited node, which is Glasgow. Now this is a bit of a shortcut we could use with Dijkstra's. In this specific example, Glasgow is the last node we explore. So it looks fine to us right now. But let's say we reach Glasgow before we explored all the other nodes. In that case, we could do something which is called an early exit. An early exit is when we find the goal cell that we're trying to get to, or trying to find a path to, and we just terminate the algorithm there. And then we could do something called backtracking, which I'll show you guys right now, to find the shortest path from the goal cell to the starting cell. Now, we don't have to explore any more cells since we are at Glasgow. We can now perform what's called backtracking. So you might have noticed that I kept on mentioning parent cells and writing it down in all of the nodes. We can use these parent cells to find a path back to the start cell, or find the optimum path back to a start cell from any node. So in this case, Glasgow has a parent node of Newcastle. So what we can do is we can backtrack to Newcastle, and Newcastle's parent node is London. So we can backtrack from Newcastle back to London. And this tells us that the optimum path to get to Glasgow from London is through Newcastle. And this is how we can use Dijkstras to solve a pathfinding problem, is by exploring the graph, finding our target cell which you want to find the shortest path to, and then we can just backtrack from there. So I hope you guys enjoyed this. If you have any questions about this topic, please leave in the description. I'll try to respond to them. And I hope you guys enjoyed the video. There's also another video I made recently about dictionaries in C. You probably enjoyed that. And this video is part of a 2-part series. So I've explained the theory of Dijkstras in this video, and in the next video I'll write down an implementation of it in C, so we can see how it actually works under the hood. So thank you for watching. I hope you enjoyed the video. Please like, comment, share and subscribe, and I'll see you guys in the next video.